Good morning, boys and girls, and welcome back. Today we are going to talk about sequences. And so let's first start off and let's talk about the difference between a sequence and a series. In this unit we'll talk about both things, but today we're going to deal with sequences, but here's the difference between the two things. A sequence is a set of terms. It looks a little something like this. Generally it looks like just a list of numbers, whereas a series is a sum of the sequence of terms. So it would look something like this. Basically, with a series, you are adding the terms together, where with a sequence, it is just a list of those terms. Okay, that is the difference between a sequence and a series. All right, and today we're just going to talk about the sequence, not the series, but eventually we'll move on and we'll start to talk about series here in a second. Well, here in a few days. Okay, and a sequence is said to converge to a limit to some value L if the limit of those terms as you go to infinity starts to approach some number, some value. Then we say it converges to that limit. If it doesn't, then we say the sequence diverges. So for instance, if you look at the sequence we have above, 2, 5, 8, 11, 14, this sequence is just continuing to get bigger and bigger and bigger, and therefore we would say that this is going to diverge. It's not approaching a value. However, I have a sequence like 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, so on. As this sequence goes to infinity, these values are getting closer and closer to 0. So we would say that this sequence does converge, and it would converge to 0. That L in this case would be 0. All right? So we're going to do a lot of looking and seeing if things converge or again, don't converge. And that's one of the main questions that we're going to try to ask ourselves. We're going to be given explicit formulas like this. A to the n equals n squared over 2n, 2 to the n minus 1. And, does this series converge or not? And so if I want to answer that question, I'm going to look at the limit as n goes to infinity. If we set this limit up and try to evaluate it, this will allow us to look at whether the sequence itself is going to converge or not. In this case, if I just roughly plug in, I get infinity over infinity. Again, if we're being lazy, we can just write, equals infinity over infinity. And that's fine, like on a multiple choice question or something like that. If this were on an FRQ, though, again, here would be the proper notation that you need to use. You'd want to include this little extra step where you're using your limit rules to take the limit of the top and the limit of the bottom. Now we can officially say that those things, that equals infinity over infinity, where this is not necessarily true. That's okay being lazy, but if we're being good with our work, it needs to look like the bottom. All right? But in this case, because it's infinity over infinity, use L'Hopital's. And when you use L'Hopital's, tell people you're using L'Hopital's, and you can do just like that. Use L apostrophe H. Everybody knows we're going to now use L'Hopital's. And we showed the prerequisites to be able to do that. And so now I'm going to take the derivative of the top over the derivative of the bottom. So the derivative of n squared is 2n. The derivative of 2 to the n minus 1 is 2 to the n ln 2, right? That's what we do in exponential, 2 to the n ln to the base, and the 1 is 0. And then now we need to reevaluate this. And in this case, again, I would say, again, I'm just going to be lazy. I'm not going to formally write it out the second time, but I would get, if I plug in infinity, I get infinity over infinity again. So now I need to use L'Hopital's twice. All right, so let's do it. When we take the derivative of the top, this time we get just 2. On the bottom, ln2 is just a coefficient. So this is 2 to the n ln2 again times ln2 again, or 2 to the n ln2 squared. But now when we plug infinity, I get 2 over infinity, which is 0. So yes, I would say that this sequence is going to converge, and is going to converge to 0. And then here's the moral of this problem and why I chose this one. But something we need to be aware of is that exponential functions are going to grow faster than polynomials. It's something that we should know. So if I have a polynomial over an exponential, we should just know, we proved it up above, but we should know that this is going to go to 0. Okay? Exponentials grow faster than polynomials. Doesn't matter the polynomial or the exponential. Similarly, another relationship we should be aware of, factorials grow faster than exponentials. Okay? They grow even faster. They get bigger quicker. So if I have an exponential over a factorial, the factorial will always win, and it'll again also go to 0. So if I'm taking the limit as n goes to infinity of k to the n, where k is just some constant, over n factorial, the factorial is going to win. It's going to get bigger faster, and so this thing would go to 0. And then, again, there's no real work to show. We just need to be aware of that relationship. And then with all this in mind, I think here's just another limit we need to be aware of. If you have the limit of 1 plus 1 over n to the n power, that might look kind of familiar to you, but we should be aware of this value here. This is actually the formal definition of e, so that would be equal to e. And then similarly, this limit here, if there's an a on top of the n, instead of a 1, then this will go to e to the a. So those we should have just some familiarity with right there, those two things. All right, let's see, a little more groundwork we got to set here. Okay, we need to talk some limit laws for sequences here. If the limit as n goes to infinity of a some sequence a sub n equals a, and the limit as n goes to infinity of b sub n equals b, then we're going to know some rules. And because these limits for the sequence are based off of actual limits, a lot of our limit rules apply here. You'll see what I mean in one sec. All right, then we have this limit rule that says if you take the limit of those two sequences added or subtracted together, then you are going to get the actual limit of those sequences either added or subtracted. Okay, so if the limit as n goes to infinity of a is 0 and the limit as n goes to infinity of b is 5, then the limit of those two sequences added together would give you 5 still, because you could add those two limits together. Another rule we have is if I'm taking the limit of a sequence being multiplied by some constant c, some real constant c, then you could just find the limit of the sequence and then literally multiply that by c, and that will give you the same thing. Okay, I'm sure we recognize a lot of these limit laws here. Our third law is if you multiply two sequences together, you could multiply their limits together. And then our last one is if you are dividing sequences, then you could divide their limits just so long as, our dividing rules, just as long as that, bottom limit is not a 0. All right, one more theorem we got to talk about. Okay, the squeeze theorem that says if the limit, as we approach infinity on f of x and g of x, if they approach the same value L, okay, I know the limit of both of those sequences or functions is going to go to L. We can apply it to either functions. In this case, I guess we're talking about functions, but we can apply it to functions or sequences. And I know that h of x is between those two functions. It's bigger than g of x, but smaller than f of x. Then I can say that the limit as x goes to infinity of h of x is also going to go to that same value, L. Basically, aka, these two functions squeeze h of x to that same value. That's why it's called the squeeze theorem. Here's a quick sketch of that theorem and kind of what's going on, so it kind of makes a little bit more sense. If we have some function f of x up on top and some function g of x on the bottom, and they're both, as we're going to infinity, they're both approaching some value L. And I know that h of x is going to be in the middle between these two things. And I don't know what h of x is doing in the middle here. Here's h of x. But as we go to infinity, it's got to get squeezed together. And so h of x also would have to approach L. Okay? So this is what the squeeze theorem is saying and what it's trying to illustrate. The squeeze theorem is a handy little theorem to use when you're trying to prove things sometimes when you can't maybe talk about the function itself or the sequence itself. You got to use, some other sequence we know that kind of bound it, and we can show that then that sequence itself gets squeezed, or series. Okay, another quick bit of vocab we got to cover here. A sequence is monotonic. Monotonic is the word you need to know. And that means a sequence is monotonic if all the terms are all non-decreasing or non-increasing. Here's an example of, something that is non-decreasing. The difference between non-decreasing and just increasing is non-decreasing means I could be increasing 3, 7, 9, but I also might stay the same. 9, it remained constant there. It didn't decrease, but it also didn't increase. So we say something like this is non-decreasing. Okay? And so this would be monotonic if it kind of kept going like that. Same thing if it's non-increasing. 1/4 over 1/16 over 1/64 over 1/56. Again, these are all non-increasing. It's going down every time. So that would also, again, be non-increasing. So this is monotonic. A series can be upper bound or lower bound, meaning it's not going to get bigger than a certain value or smaller than a certain value. In this case, this series is bounded above by 1. It's not going to get bigger than 1. And it's bounded below by 0. So in this case, it's bounded on both sides. And if it's bounded above and below, then we say that series is bounded. And I just realized right there, again, I got to be careful. I realized I said series is bounded. I meant sequence is bounded. Also, I just noticed when I recognized that mistake, I noticed I put series up here instead of sequence. So I'm going to go and fix that. But here we're talking about sequences. So if a sequence is bounded above and below, then we say it is bounded. All right. Here's our last theorem. If a sequence is bounded and monotonic, then we know it converges. Okay, so if we have a sequence that is bounded and monotonic, then we know it's going to be, then it converges. Like the one we're looking at right above here, that is bounded above and below, we said, and it's monotonic. It is non-increasing. Therefore, that sequence is going to converge, and we said already we knew that. It's going to converge to 0. So quick little amendment to our theorem that we should know is that all convergent series are bounded, but not all bounded sequences are going to converge. Okay, so it's not exactly the same thing, and here's a quick example of that. The sequence -1 to the n would give us -1, 1, -1, 1. This is a bounded sequence above and below, bounded below by -1 and above by 1, but this is a sequence that is not going to converge to anything. It just bounces back and forth. Okay, so similar, but not exactly the same stuff. Okay, so let's do some problems now. We want to find the limit of the following sequences. So if I want to find the limit of this sequence, I'm going to take the limit as that goes to infinity. And then remember, as we go to infinity on a limit, we really don't care about like the +4s. That's not going to do much, so I could rewrite this or think about it as n to the 12th over 3n to the 12th. And then those n to the 12th would cancel out, and we'd be left with 1/3. So that would be the limit of this sequence. All right, so here's our next one. We want to see if this sequence is going to converge. So we're going to take the limit as n goes to infinity. Because it's going to infinity, again, I can forget all the plus minus stuff. So we get 5n over the square root of n squared, which is 5n over n, which is just 5. And again, kind of just showing what I'm thinking about as I'm evaluating this limit analytically. So that limit would converge to 5. Okay, one more of these. What is this sequence going to converge to? Taking the limit as n goes to infinity, and then we're going to be a little lazy here with our notation, but ln of infinity is infinity over n is infinity, so use L'Hopital's. Before I use L'Hopital's, I think I would rewrite the top, pulling, making the square root an exponent and pulling out in front using log rules. This will make my derivative life a little bit easier. And then I get, when I take the derivative of the top and the bottom, 1/2 times 1 over n over 1, or 1 over 2n, and now this is going to go to 0. Next, we're going to practice writing an expression for the nth term, okay? Or our, explicit formula for this. And when you do this, you want to start by trying to look at patterns. So it looks like I'm going up by 4 every time here. And again, this just takes practice a little bit, but when you look at that pattern, what it's going up by, there's an arithmetic sequence. So I can generally, that becomes my slope for n minus 1. And that looks like that'd be the arithmetic sequence, but it just takes practice playing around with this to come up with those. Here is another one. Some little tricks we use on ones like this. If it's switching back and forth on signs, you might try something like this. Take -1 and raise it to a power. Now, if I plugged in a 1 here for the first term, it's going to make it negative, so I need to just adjust that a little bit. Now, n plus 1 would make it positive. And then on the bottom, we can see that we have perfect squares. So this might be, n squared. And so just play around with this stuff, and it'll make the more practice you get, the easier it'll become. Okay, next now we want to look at these following sequences, see if they're bounded, monotonic, or both. So my advice would be to first write out the sequence, or at least the first few terms. In this case here, when we look at these terms, the terms are increasing and then decreasing and then increasing, so it's going both directions. So this is not monotonic. But I would say that it is bounded. I'm at -2/3 and then +4/9, and then every time these numbers, as I raise them to higher power, they're really getting smaller, and I could say this is eventually going to converge to 0. So it's not monotonic, but it is bounded between -2/3 and 4/9. See you later. Have a nice day.